Hi, in this video I'm going to solve 3 problems about the normal force. So let's start with number 1. Let's just zoom in a little too much. Number 1, a 50 kilogram person is standing stationary on horizontal ground. Find the normal force acting on that person. So we're going to start, as always, with a free body diagram. This is my person. There are 2 forces acting. Gravity is pulling down, mg. And the normal force pushes up, Fm. We also know that our person is stationary, so their acceleration is equal to 0, and our velocity is equal to 0. So now we just need to set up Newton's second law and solve. Sum of the forces, in this case it's the y direction, equals mass times acceleration. Sum of our forces is going to be our normal force in the positive direction minus mg. Mg is in the negative direction, equals mass times acceleration, which means our normal force is equal to ma plus mg. When we solve that, if we plug in our numbers, since our acceleration is equal to 0, ma goes to 0, which means our normal force is just mg. That's mg, and our mass is 50 kilograms. And g is 9.81 meters per second squared. When we plug that into a calculator, we get 50 times 9.81, 490.5, or to 2 sig figs, our normal force is equal to 490 newtons. For the simplest case, our normal force is just equal to the force of gravity. Okay, let's move on to question 2. Jennifer, who has a mass of 42 kilograms, steps into an elevator to get to her 7th floor dormitory. The elevator begins to accelerate upward at a rate of 2.2 meters per second squared. Find the normal force acting on Jennifer during the acceleration. Now keep in mind we are diagramming Jennifer. Jennifer is just standing on the floor, so she's going to feel the force of gravity, of course, mg. And there's going to be an upward normal force, Fn, from the bottom of the elevator. Now it tells us that the elevator begins to accelerate upward. So I'm going to label that there's an upward acceleration of 2.2 meters per second squared. Oh, and if our acceleration is upward, then our net force is up, which means, well, the normal force has to be stronger than gravity. So I'm just going to adjust the length of that vector, make it a little bit longer. Just so hopefully we can see, how about we make gravity a little shorter? Hopefully we can see that normal force is greater than gravity. Then again, we just set up Newton's second law of motion. Sum of the forces equals mass times acceleration. We choose the direction of the acceleration to be positive, so we're going to say up is positive in this case, down is negative. And my positive force is normal force minus mg, force of gravity, equals ma. Now, this is the same as the previous problem, so when we solve it, we'll get the same as the previous problem. The normal force is going to end up being ma plus mg. Or if we wanted to factor that m out, it would be m times a plus g. In this case, the normal force has to be greater than gravity by an amount equal to the net force, or mass times acceleration. So all we got to do is plug in our numbers. Our normal force then is equal to mass, 42 kilograms, times a, which is 2.2 meters per second squared, plus g, plus 9.81 meters per second squared. Let's plug that into a calculator. Do the parentheses first, 9.81 plus 2.2. 12.01 times 42 is 504, so to 2 sig figs, that's going to be 5.0 times 10 to the 2. It's about 500 newtons. That's that. Okay, next. This third problem is actually a 2-dimensional vector problem. So you're going to have to know how to take vector components in order to do this one. A 0.70 kilogram block of ice slides down a frictionless ramp that is at an angle of 20 degrees above the horizontal. Find the normal force acting on the block. So I'm going to sketch out my free body diagram. And I'm going to just label this as 20 degrees. My block of ice is on this at an angle. There's a downward force equal to mg. And the normal force points perpendicular to the surface. Normal force. It's frictionless, so there's no friction. These are actually going to be our only two forces. So to solve this one, we're going to need to break our vectors into components. And before that, we need to choose an x and y direction. And the best way to choose an x and y direction is going to be choose x to be along the direction of the slope, which means y is perpendicular to the slope, positive y. That's going to be easier because then our acceleration is just going to be in the x direction. Since gravity is pulling down, our acceleration is going to be down the slope. Okay, so by choosing our coordinate axis to be parallel and perpendicular to the slope, the normal force is already in the y direction, but our gravitational force is not in either the x or y direction. So we need to break that into components. I'm going to do my components in blue. As we break our vector into components, we're going to draw a right triangle. The resultant vector, or the total vector, is the hypotenuse, and the components are the legs of our right triangle. So this is mg y. This is mg x. Now to solve for mgy and mgx, we're going to have to use some trig to figure out what one of these angles is. So let's do that in red. I'm going to use some geometry. This is up the slope. This is 20 degrees. This is a right angle right here. So that means this other angle is going to be 70 degrees, which means this is 20 degrees. Okay. So let's actually redraw this triangle off to the side and solve for everything we can. Right angle, 20 degrees. That means this bottom one is 70 degrees. Okay. Let's see. So this is mg. And from trig, this leg over here by the 20 is going to be mg cos of 20 degrees. This is going to be mg sine of 20 degrees. So, yeah, that's fine. Let's just set up Newton's second law in the x and y directions. So let's go down. In the x direction, sum of the forces in the x is equal to mass times acceleration in the x. Well, the only force acting in the x direction is mgx. So it's just going to be mg sine of 20 degrees is equal to m times our x acceleration, which is our total acceleration. And in our y direction, well, actually, we could use that to solve for the acceleration if we wanted. In our y direction, sum of the forces in the y equals mass times acceleration in the y direction. Well, we have two forces in the y direction. We have the normal force pointing in the positive y, and the y component of gravity in the negative direction. That's mg cos of 20 degrees. And that's equal to mass times acceleration in the y. But it's not accelerating into the surface or above the surface, so our acceleration is just going to be equal to 0, which means that the normal force is equal to mg cos of 20 degrees. We plug in our numbers. Normal force is equal to m. M is 0.070. Actually, it's 0.70 kilograms. G is 9.81 1 meters per second squared times cos of 20 degrees. And we plug that into a calculator, make sure we're in degree mode, since we're using degrees as our angle. 0.7 times 9.81 times cos of 20 gives me normal force of 6.39 newtons. Now, notice in this case we didn't actually need the Newton's law in the x direction because there was no reference to the normal force there. We didn't need that at all. All we needed was the y direction. However, if we wanted to solve for the acceleration, we could use the x direction to get that. It's just going to be g sine of 20 degrees. That's that. We break our vectors into components, we do Newton's second law, and we are good. Anyway, that's 3 problems on the normal force. Hope that was helpful. Goodbye.